Hi everyone, welcome to discussion 8 for CSE 100. This is going to be going over project 1, the final submission. Alright, so here's an overview / the table of contents. Each of these are links. As usual, I'll be posting the slides below so that you have access to this and can go back through the slides on your own. So I'm going to talk about CMakeLists.txt, IO buffering, BitOutputStream, BitInputStream, testing those, Encode and Decode with Bitwise IO, and then trueCompression and trueDecompression, efficient header design, and then some miscellaneous stuff that I think would be beneficial. So some notes: there are hidden tests for your final submission, but they are listed in the rubric. This comes across a little bit strange. So what I'm saying is, in the rubric for the final submission, the only tests we will be running are the tests listed on the rubric. But when you submit to Gradescope, some of those tests aren't actually going to be run until after the final deadline. Therefore, you need to actually test these on your own and I believe come up with the test files as well. And then this is just a reminder. I know I said this in the previous video, but for code coverage, Encoder and Bitstream directories are going to be included for the final submission. So to get that 90% code coverage, it needs to include both of these directories. Okay, so resources, this is essentially the exact same from last time. I will say that please look at the Piazza frequently asked questions and the other posts. There were a lot of duplicates for the checkpoint, so please just look at these. There's a lot of good feedback and help there. Okay, so what do you need to do for project 1 final? For part 1, you need to write the CMakeLists.txt for the Bitstream directory. Then for part 2, you need to implement BitOutputStream and BitInputStream. Then you need to test these using the Bitconverter. Obviously, you're not required to test, but testing is good and you really should. Part 4, implementing code and decode with Bitwise IO. And then part 5, efficient header design. Also, please don't forget to fill out your final reflection for this project. Thank you. All right, so for CMakeLists.txt, all right, the resources, they're in the document, the final project write-up as well, but I just posted them here as well. There's the CMake concepts and then the full documentation as well. So for writing your CMakeList.txt, you need to do it for all of the subdirectories in source/bitstream, and you need to uncomment some things that are in the CMake lists. So where do you need to add these CMakeList.txt? For all of the subdirectories. This means in the Bitstream directory directly, in the input directory, and in the output directory. Also, when you create the CMakeList files in input and output, you need to create a library with these specific names. So bit_input_stream and bit_output_stream. That's because there's a different location, which you'll be uncommenting, that uses these library names. You need to use them exactly when you add these libraries, which is something you should be doing in these files. As some hints, you should look at the source encoder CMake lists, and that'll give you some ideas for the input and output files. And then also source CMake lists, that file is the one where BitInputStream and BitOutputStream, these library names are defined. And you should think about how input and output are subdirectories of Bitstream and what that means for what you need to be putting in these CMake list files. Okay, so where do I need to uncomment code? You need to do for CMakeList.txt, those are the ones under source, the source directory, under the encoder directory, and under the test directory. And then there's also some stuff you need to uncomment in HC tree. So you need to uncomment the includes Bitstream and the encode and decode. All right, so some stuff for CMake that you should know. I know we kind of went over this last time, but for add directory, that means, hey, CMake, this directory also contains code that belongs to my project. Please look at the CMake techlist file inside the directory to see what to do with it. So this is something that, as we mentioned, right, certain things are directories, subdirectories of others, so this might be relevant to you. Then adding a library, hey, CMake, here's a bunch of code that is not directly executable, however, it can be imported by other code. Please bundle it in a library so that our other build targets, library, executable, etc., can include this code using target links libraries. So target link libraries, hey CMake, I have a build target, library, executable, etc., that depends on a library called XYZ. And then target include directories, that's saying, hey CMake, I have a build target, library, executable, etc., which wants to include some header files which are in this directory. All right, so then public and private. So public means please share these libraries and include directories with build targets that depend on me. And private means please do not share these libraries and directories with build targets that depend on me. Okay, so now I'm just gonna actually pull up the VS Code and show you the files that you need to make changes to and how you should make everything once you update your CMakeLists.txt, and we'll create them and then update the ones that need to have some things no longer commented out.
Okay, so I'm just going to show you what you need to uncomment first. So first we want to uncomment things in our different CMakeList.txt, right? So this is the top level one, and we actually don't need to make any changes here. But then inside of source, the one directly under source, you need to uncomment the add directory there, and then also these two here, right? And then you need to go under the encoder directory and uncomment this. And finally, under test, you need to uncomment all of these, right? Okay, and then in addition to that, if you go into hctree.hpp, we have these two includes that we need to uncomment, as well as now we're using BitInputStream and BitOutputStream. And then we need to uncomment these, as we are now using the encode and decode that use BitInputStream and BitOutputStream. And then in hctree.cpp, we need to uncomment these functions as well, as this is where you will be implementing them. All right, so that should be it in terms of what you need to uncomment. But in addition to that, you need to go into the Bitstream directory and you need to create CMakeLists.txt here, right? And then you need to make one in both of these directories. Okay. Okay. And you can see, right, we have these different ones here, and these are the ones that you are going to have to create yourself, right? So these three, we suggest taking a look at the one in the encoder directory just to get a sense of what you're supposed to do, though it will be slightly different, as you essentially have Bitstream at the same level of encoder, but then you have these two other folders inside. So we give some references and ideas, but this is a good starting point to think about, and think about the fact that input and output are subdirectories of the Bitstream directory. So that is it in terms of how you should set it up. Also, don't forget you're going to have to rebuild and everything because you've added these and your CMake lists have changed. Okay, so now I've already implemented these three CMake lists, though I'm not going to show you, as you're supposed to implement them yourself. So now that I've done that, what you need to do is you need to cd into the build directory. As you can see, I did that. The first time I did it, right, I got an error, and that is because some of you may have noticed before when I created the CMake list files, the L was lowercase, not capital, which caused this error. So now what you do is, once you've updated everything, make sure your file names are correct. Go into the build directory and then you run CMake, and ta-da, done. And then you can run make. And you're good to go, assuming that your CMake list files were created correctly.
Okay, so I/O buffering. So for C++, we have these bitwise operators that you should have learned in CSE 30, right? We have the logical operators and, or, XOR, and not, and then the shift operators as well. So operands to these operators can be found of any integral type. So for these, right, we have AND, which does the bitwise logical AND of its arguments, OR, which does the bitwise logical OR, XOR for the bitwise XOR, and then the logical complement. And then we also have these shift operators. So this is all going to be important to you for when you want to read and write bits. So the first one shifts its left argument by a number of bit positions given by the right argument, and it shifts zeros on the right. So when you shift left, there will be for the amount of spaces you shift over, whatever's on the end is going to be cut off, but then you'll have these new zeros on the right-hand side. And then it's the opposite for shifting the argument the other direction. So these are the different operators. I know I just showed them to you on the other side, but this is just a more concrete, simple thing to look at. Okay, so here is a simple I/O exercise just to get you back in the mindset / mode for this. So which of A, B, C, and D would correspond to these different operations on X and Y? So I would suggest pausing the video now and trying to figure it out on your own. I'm just going to move forward as usual, but please do pause and try to do this on your own. Okay, so the answers are B, C, and A. Okay, and if you don't understand these, feel free to post on Piazza with a question and we can help you there. Okay, so now C++ bitwise operator. So selecting a bit. Suppose we want to return the value 1 or 0 of the nth bit from the right of a byte argument and return the result. How would we do that? So once again, I would suggest pausing the video. I'm just going to move forward, but please do try to figure this out on your own, as it will definitely help you with the assignment and with write and read bit. All right, so this is what it would look like. If you did take CSE 30 with us, please feel free to look back at your notes. They might benefit you. And if you have questions about this, please post on Piazza as well. You're also free to look up resources to better understand what bit shifting is and what the operators are. Okay, so what is the raw data of this file? Right, so we have in this example nums, right? We have 1, 2, 3, 4. And really in binary, right, these correspond to these binary values. Okay, so this is just kind of trying to show you how this 1, really in binary it's this. So these are the different bits that make up this 1, right? And we'll talk more about this, or it'll be referenced later on. Okay, so buffering and bit-by-bit I/O. So the standard C++ I/O classes do not have any methods for doing I/O at a bit at a time, which is what we're going to want to do. The smallest unit of input or output is 1 byte, which is 8 bits. And remember that 1 byte is 8 bits, as that will be relevant in your assignment as well. Now, this is standard not only to C++, but in just about every language in the world. If you want to do bit-by-bit I/O, you need to write your own methods for it. So the basic idea is to use buff size as a blank byte buffer, right, bit, not byte, buffer, and I'm writing blank because, right, it depends on what buff size is, so it's really buff size bit buffer. So you're going to be using bitwise shift and or operators to write individual bits into the byte and read individual bits from it. And you're going to flush the byte when it's full or done, right? So basically, you know how we've been encoding everything with zeros and ones that are characters? Now we're going to be doing it with actual bits. All right. So this is kind of an overview of what it'll look like. So we are going to be using BitOutputStream and BitInputStream, which you should be implementing. So essentially our encoder will call BitInputStream, which will use OStream, and then eventually that will be written to the disk. And then you can manually flush. And then it'll be the opposite direction, right, for us using BitInputStream to decode. Right, so this is just an image here to kind of help you make sense of it. But we're going to go into BitOutputStream and BitInputStream now, or in a minute. So flow between streams and buffers. So writing bits to a file, right, it'll be the encoder to the buffer to OStream, buffer, and then disk. And the in-between buffer is the buffer that we created, right? So encoder, our buffer, etc. And then for reading bits from a file, it will be the opposite direction, right? So this is just another visualization for you to try to understand it. Okay, so now let's look at BitOutputStream. So what is a BitOutputStream? It consists of a reference to an output stream to use, a buffer of character arrays, or a character array which will represent our buffer, the size of the buffer in bytes, the number of bits that have been written to that buffer, and then it might also, it's not part of it, but it might also be nice for you to have something to keep track of the total number of bytes written out. That's a suggestion, but it's not a field that already exists. But it could help you. All right, so I'm just going to step through what each part corresponds to. So when we're going through the constructor, what fields do we need to set? So, right, the out corresponds to the OS stream that is being passed in. Buff is an array of characters, and the size corresponds to buff size, which is what's also being passed into the constructor. Then we have the unsigned int buff size, right, and that is going to be the argument passed in exactly. And then n bits, so the number of bits that have been written to the buffer. So when we construct BitOutputStream, have we written anything to buff? What should we set n bits to? So that's a question I will leave with you. All right, and so here we're actually giving you more or less what the constructor is, but I want you to understand what each part represents, as that is going to be important when you're actually using and interacting with these, right? Okay, so what is flush? When and where should flush be called? It should be called in write bit. There might also be some other places, but that's up to your implementation and how everything goes. So inside of flush, here's kind of a template to start with, but you should use n bits to determine how many bytes to flush. So first you want to determine what flush size is, and then you're going to want to flush the buffer, right? And then you're going to want to clear the buffer and the bit counter. And if you do keep track of byte size, you might want to increment it here, but that is up to you. Okay. And then write bit. So you're going to write the least significant bit of the argument to the bit buffer and increment the bit buffer's index. But flush the buffer first if it's full. So first you need to check if the buffer is full. So you need to think about what that entails and how you do that. Then you need to write the least significant bit of I into the buffer. And here's just some ideas of what you could be, of how to do it, but those question marks you need to figure out on your own. And you might want to use some Bitwise logic. All right. So when and where should write bit be called? In compress and encode. But once again, depending on your implementation, you may call it in, well, you probably should call it in these places, but yeah. All right, so BitInputStream. BitInputStream and BitOutputStream are listed here. I guess this slide got moved to a different position. I'm just going to leave it here for the sake of not re-recording. But essentially, BitOutputStream should be used in trueCompression and Encode, and BitInputStream should be used in trueDecompression and Decode. And these are the different methods that you'll be dealing with. So I already kind of went over BitOutputStream, but I'll go over BitInputStream now. Sorry for having the slide out of order. All right, so what is BitInputStream? So there's a reference to the input stream to use. This is going to be kind of similar to BitOutputStream. Then the buffer, buff size, n bits, and then the end of file bit. So for the constructor, this is also a similar setup, right? And this just kind of goes over what we care about in here. So here the thing is for n bits, right? It's how do we convert it to, buff size to bits is essentially the question. As we mentioned earlier, right? A byte is 8 bits, so that is relevant to that part. And then the end of the file bit. When we construct BitInputStream, have we reached the end of the file? So think about that. Now, once again, we're providing you essentially with the constructor, but it's important to understand what everything is and what's happening. Okay, so fill. So for fill, this is what your fill method should look like. You need to read in to the buffer, buff size, and when the buffer is full and ready to read, you're good. And you've read 0 bits. All right. So for Bitstream at end of file, you should look into a G count. There's a little bit of a link there. So you need to think about, so this should return true if you're at the end of the file, otherwise false. So how can G count help us? What does it mean if G count returns 0? And how can we compare G count and bits? So where should we use this end of file? In read bit. Okay, so BitInputStream read bit should be used in decompress and decode. And you should think about, what do you do if all bits in the buffer have been read? What do you do if you've reached the end of a file? And this read bit should be somewhat of the opposite of write bit, right? Because you're going to be encoding it and then decoding it, or putting it into a byte and then extracting it out of that byte. So you can kind of, once you write your write bit, you can kind of use it to write your read bit as well, or opposite order, whatever works best for you. Okay, so testing, I'm just going to say something small about this. So here's some examples. They're in the write-up, but I just wanted to show them here. So here's 2 examples for that, but please read the write-up to understand how you can use Bitconverter. Please use Bitconverter. It will be very beneficial to you, and you should definitely make sure that your BitInputStream and BitOutputStream work before you move forward, right? Now, testing against the reference solution, you should use diff to compare. This is what you should have been doing for the checkpoint as well. I just wanted to mention it again, and that's the executable. You should be using the reference executable. Encode and decode with Bitwise IO. So what you need to implement, there are these 2 new functions for encode and decode. For encode, write bit might be useful, and for decode, read bit might be useful. And overall, these methods will be really similar to what you had before, but implemented a little bit differently depending on how you choose to encode and decode. But the main thing is that these are using real bits instead of characters, right? In our other encode and decode, we're just outputting bits, or outputting characters, but here we're using actual bits, which is a very important difference, and we'll make it so we can actually compress our file properly. So how are encode and decode different? I just said this, but we're using bits, and this is just a little bit more information. It's kind of just reiterating what I already said. So true compression and true decompression. What's the difference between pseudo and true? So for one, we're using buff size. We're using real bits, so we're using BitOutputStream and BitInputStream, and our header should be optimal. So we shouldn't just be listing these frequencies. So in our header where we have line 0 through line 1 through 256, just listing the frequencies of the ASCII values, that's just not really going to compress our file. And as you may have noticed, if we wrote something like A in a file and compressed it, the compression would be so much bigger than the file we're trying to compress, which just isn't logical and doesn't really achieve what we're trying to achieve. Okay, so for compression and encoding, the main difference here is that for the pseudocode, we're going to open the file using OFStream, and in the true compression, we are doing that as well, but then we're creating our BitOutputStream, right? And you need to come up with an optimal way of storing the tree and the message. All right, so then for the pseudo, right, for ours, we're not going to have these 256 lines of frequencies, right? As I just mentioned, that is definitely not optimal. So you need to come up with your own optimal way of doing it and doing it in bits. And then for the characters, we're going to be actually the decode. It'll be the decode corresponding to our optimal header. Yeah, but these are going to be based off of your implementations, and you need to make design decisions on your own. There is no one way of doing this. Okay, so for testing your compression, now your header and the reference solution header should not produce the same compressed file, right? Your goal is to beat the reference solution. Your compressed file should be better than the reference solution. And therefore, you should not use diff here because the output of the compressed file should not be the same. Though it might be a good starting point to just try and implement the version described in the write-up as the reference, just so you know everything's working as expected, and then from there, go on to try to think of how to do it optimally. Also, I would suggest starting to think about making it optimal as soon as possible, just because depending on how in-depth you want to go, it might take a while to come up with your final implementation for the header. Okay, so please note, your header is going to look like nonsense, right? Because we're using bits, not bytes. So going back to that example where we were looking at the bits that represented 1 or 2 or 3, right? We're going to be just like using the bits directly. So we're going to be making these nonsense characters that don't really have a value to us. But underneath those nonsense symbols are actually holding the bit values that we wrote and that have meaning to us. So that's just something to keep in mind. You can't just look at the file and be like, oh, this makes perfect sense, which you were able to do for the previous one. You could just look at the header and kind of get a sense of what was happening. That won't be possible for this. Okay, so now moving on to the efficient header design, which I kind of already just went into, but this will give you much more detail. So for the naive encode and decode procedure, right? These were the two things that we were doing in the step. So first, scan the text file to compute frequencies, build the Huffman tree, find code for every symbol, and then create a new compressed file by saving the entire file at the top of the file, followed by the code for each symbol. And then for decode, we'd read the file header to recreate the tree, and then decode each letter by reading the file and using that tree. So these are the steps that are going to be a little bit different. So for writing the compressed file, in order for your uncompressed program to know what the Huffman tree looks like, you need to store some information, right? So that it's able to recreate that tree, rebuild it. So you need to store some information at the top of your compressed file to let the uncompressed program rebuild this tree, right? But the way we have it with these frequencies being stored, that is really, really time consuming, okay? So it's just not a very good approach, and we need to come up with a better approach. So we do need to store some information if we want to do this, but we don't need to store it on 256 lines, right, and have a character on each of these lines. Okay, so realistically, why are we trying to reuse build? That's kind of strange. We need to rethink our strategy and what we're trying to achieve. So is there a way that we could somehow rebuild the tree based on some clues that we bury for ourselves instead of rebuilding from these counts? Is there a way that we could encode the tree itself into our file? And that is what you may try to do. So store the tree directly in the header. That is probably the best solution. And you do need to beat the reference solution, and the reference solution doesn't do this. So think of how you could do this. How can you store the tree directly in the header? What aspects of the tree allow you to do this? What are the properties that can benefit you? So suggestions for encoding the tree. Take a good review of how much space you need for a number, symbol, any of the info you need to take, right? Think about the properties of the Huffman tree, and think about how you can best use your iterative and recursive rebuild structure. Also, you should avoid using delimiters. It may end up using more space. So don't just put a bunch of things on a new line. See if there's a way that you can put the majority, if not all of the information you need on a single line. Okay, and then finally, miscellaneous. These are just some things that I thought would be beneficial to go over very quickly. How do I test functions in compress and uncompress? We kind of went over this before, but it works just like file util. So you can add a file called helpermethods.hpp. Honestly, though, it'd probably be better to name it something more reasonable, like helper methods of what. This doesn't really give you any information. So name your file in a smart way. Then move the methods you want to test into that file. And then in this CMakeList file, add helpermethods.hpp to the list of files in add executable for compress and uncompress. And then you can include the file in uncompress and compress with an include statement. And that way you can test your helper methods. And I just want to reiterate, helper methods are amazing, right? You can test them. You can know that they work. And once you know they work, if your program breaks, you know that that is not what's causing it. It allows you to incrementally test your program and also kind of decrease the space in which you are working and unsure of. So please use helper methods. Helper methods are amazing. I love them. Also, just in general, depending on how you're using, creating the tree in your header, recursion is going to be a big deal, and you might have to do multiple recursive things. So having helper methods do each of those will just make it a lot easier to test and make sure you're building the tree correctly. Okay, so for grade scope, you can assume that the input file is less than 2 gigabytes, which means a particular symbol may appear 2 billion times. So the maximum symbol counts may have an influence on the header, because if you implement it using integers, then there's a maximum count an integer can represent. This indicates that using counts in the header is perhaps not the best idea. We're trying to get students to think about encoding their tree in the header instead of listing the counts. So please try to encode the tree rather than listing the counts that are available. Also, you might want to have different cases, like, oh, if there's only a single character in a file, is there a better way that I could deal with this situation? Is there a way that I could write my header to notify myself of that and make it even smaller, right? And so you can kind of just think about, there might be multiple cases due to how you want to write your header, how you want to write your header. Like there is no one answer for how you implement this. Okay, so that is it. Happy coding. I hope this was helpful. If you have any questions, please post them on Piazza, and we would be more than willing to help you out.